In this unit, we're going to talk about Bohr diagrams some more, and we're going to move on to Lewis dot diagrams. They're also called electron dot diagrams. And finally, we're going to talk about ground state versus excited state. In this video, we're going to talk about Bohr diagrams, Lewis dot diagrams, but we're not going to get to ground state versus excited state. That will be in video 2.6. The Bohr diagram shows the nucleus, and it indicates the number of protons and the number of neutrons. And here you can see I've drawn the protons with a positive and the neutrons with a 0 charge. So the net charge of this nucleus is positive 6, and that's why out here on the rings you need a total of 6 electrons to balance out that positive charge. This is a regions question that I found, and it's the only one I could find that had a Bohr model in it. It tells you that this particular nucleus contains 4 protons and 5 neutrons. From that, we should be able to figure out the atomic number and the mass number. 4 protons would be the atomic number, and 4 plus 5 would give us a mass number of 9. This element would be beryllium because each element has its own unique atomic number, and beryllium is the only atom with 4 protons. The Bohr diagram here has the nucleus in the center, and then each of the rings are numbered. This is ring n equals 1, n equals 2, n equals 3, and n equals 4. In some sources, they also give these rings the letters K, L, M, and N. Theoretically, in a Bohr diagram, we could go all the way up to 7 shells outside of the nucleus. Each energy level has a maximum number of electrons that it can contain. We use the formula 2n squared to figure that out. If we replace the n in the formula with the number of the energy level and do the math, it tells us that energy level 1 has a maximum of 2 electrons. Energy level 2, a maximum of 8, and energy level 3, a maximum of 18. Put this in your notebook and then practice how many electrons would energy level 4 hold. Using this formula, we're going to plug in a 4 in place of the value n, and we get 32. Now, the formula 2n squared only works for n equals 1 all the way through to n equals 4. Once we get to the 5th, 6th, and 7th energy level, they all hold 32 electrons each. The octet rule, which we have already talked about a little bit, states that an atom reaches a point of stability when it has a set of 8 electrons in its valence shell. Remember, the valence shell is the outermost shell where the electrons are found. All of the noble gases except for helium already have an octet. Helium only has 2 electrons. All of the other elements on the table will either lose or gain electrons in order to obtain an octet. What about those energy levels that can hold more than 8 electrons? Remember, the 3rd energy level can hold 18, and the 4th energy level can hold 32? Well, we're going to talk about that. I'd like you to follow along as we show the electron configuration. Sulfur, chlorine, and argon are all in the 3rd energy level, so the electron configuration shows 3 numbers. The first number, 2, tells me that primary energy level 1 is filled up, primary energy level 2 is filled up, but primary energy level 3 only has 6 electrons. It's not yet filled. 2, 8, 7, 2, 8, 8. Is the 3rd energy level filled up to capacity? No. It can hold as many as 18, but we stop at 8 because it represents a point of stability. Now let's go over here. We're at the beginning of the 4th row on the periodic table. We call this period 4. So all of these elements will have 4 digits in their electron configuration. That means there's electrons in 4 shells. The first shell is filled, the second shell is filled, the third shell is temporarily filled with 8, and we have started filling the 4th shell. Calcium has the same thing. Full, full, temporarily held at 8, and 2 electrons in the 4th shell. Now look carefully at what happens to scandium. That third number is starting to get bigger. The 3rd shell we're starting to fill with electrons. And as we move across, we see that we add more electrons to that 3rd shell. The 1st, the 2nd, and the 4th shell are being held constant. And we're filling up that 3rd shell. At some point, we even borrow from the 4th shell because it's more stable. For chromium, we wanted to put 13 electrons in the 3rd shell, and to do that, we had to borrow 1 of our electrons from the 4th shell. Another point of stability that we get to happens with copper. So let's move down the line. Look here, copper is the first element that has completely filled the 3rd principal energy level. To do that, we had to borrow 1 of the electrons from the 4th energy level to do that. Another exception to the octet rule is called the duet rule. The first 5 elements on the periodic table will not be able to have an octet in their valence shell because they're either losing electrons from the 2nd shell or adding electrons to the 1st shell. For example, lithium. It's our 3rd element. The electron configuration is 2-1. When it loses 1 electron, it becomes a +1 ion, the electron configuration becomes 2. So it does not have an octet because we're dealing with elements that have electrons in the 1st shell and they can't achieve an octet. Up until now, we've always talked about the atom having 2 parts. The nucleus, which is the center of the atom and positive, and the electron cloud. Now we're going to look at the nucleus and the inner electrons, and we're going to call that collectively the core. And the valence shell is the only part of the atom that really gets involved in the chemistry. When 2 atoms come close to each other, it's the electrons in their valence shell where all of the chemistry happens. We don't change the nucleus, and unless we're certain elements on the periodic table, we generally won't touch the core electrons. The valence electrons are the electrons located on the outermost ring, and the valence number will always be somewhere between 1 and 8. So let's look at these elements here. Boron has a valence number of 3. Carbon has a valence number of 4. Nitrogen has a valence number of 5. Oxygen 6. Fluorine 7. And neon 8. So the valence number is the last number in that electron configuration. When we draw Lewis dot diagrams, sometimes they're called electron dot diagrams, we only draw the valence number. Remember, we said lithium had 3 electrons. 2 are the inside electrons, and 1 is the valence electron. So lithium only has 1 electron dot because that's the outermost or the valence electron. Beryllium has 2, the next element, beryllium. It's the 4th element, 4 protons, 4 electrons, but only 2 dots because we're only looking at the valence electrons. I was going to talk a little bit about ground state and excited state here. We're going to introduce it in the next topic. When you look at an element symbol, the electron configuration that they show on the table is ground state. If it's anything other than this configuration, then it's not ground state. We'll talk a lot more about this in the next video.